and and yet a systematic, disciplined, and quantifiable approach applied by one software team may be burdensome to another. We need discipline, but we also need adaptability and agility. Software engineering is a layered technology. Referring to Figure 1.3, any engineering approach, including software engineering, must rest on an organizational commitment to quality, total quality management, Six Sigma, and similar philosophies. First, foster a continuous process improvement culture, and it is this culture that ultimately leads to the development of increasingly more effective approaches to software engineering. The bedrock that supports software engineering is a quality focus. The foundation for software engineering is the process layer. The software engineering process is the glue that holds the technology layers together and enables rational and timely development of computer software. Process defines a framework that must be established for effective delivery of software engineering technology. The software process forms the basis for management control of software projects and establishes the context in which technical methods are applied. Work products, models, documents, data, reports, forms, etc. are produced, milestones are established, quality is ensured, and change is properly managed. Software engineering methods provide the technical how-tos for building software. Methods encompass a broad array of tasks that include communication, requirements analysis, design modeling, program construction, testing, and support. Software engineering methods rely on a set of basic principles that govern each area of the technology and include modeling activities and other descriptive techniques. Software engineering tools provide automated or semi-automated support for the process and the methods. When tools are integrated so that information created by one tool can be used by another, a system for the support of software development called computer-aided software engineering is established. Crosstalk is a journal that provides pragmatic information on process methods and tools. It can be found at www.stsc.hill.af.mil. Software engineering tools provide automated or semi-automated support for the process and the methods. That when tools are integrated so that information created by one tool can be used by another, a system for the support of software development called computer-aided software engineering is established. The software process. A process is a collection of activities, actions, and tasks that are performed when some work product is to be created. An activity strives to achieve a broad objective, for example, communication with stakeholders, and is applied regardless of the application domain, size of the project, complexity of the effort, or degree of rigor with which software engineering is to be applied. An action, that is, for example, architectural design, encompasses a set of tasks that provide a major work product. For example, an architectural design model. A task focuses on a small but well-defined objectives. For example, conducting a unit test that produces a, a tangible outcome. In the context of software engineering, a process is not a rigid prescription for how to build computer software. Rather, it is an adaptable approach that enables the people doing the work, the software team, to pick and choose the appropriate set of work actions and tasks. The intent is always to deliver software in a timely manner and with sufficient quality to satisfy those who have sponsored its creation and those who will use it. What are the elements of a software process? A process defines who is doing what, when, and how to reach a certain goal. Ivar Jacobson, Grady Booch, and James Rumbaugh. A process framework establishes the foundation for a complete software engineering process by identifying a small number of framework activities that are applicable to all software projects, regardless of their size or complexity. In addition, the process framework encompasses a set of umbrella activities that are applicable across the entire software process. A generic process framework for software engineering encompasses 5 activities. Communication. Before any technical work can commence, it is critically important to communicate and collaborate with the customer and other stakeholders. The intent is to understand stakeholders' objectives for the project and to gather requirements that help define software features and functions. Planning. Any complicated journey can be simplified if a map exists. A software project is a complicated journey, and the planning activity creates a map that helps guide the team as it makes the journey. The map called a software project plan defines the software engineering work by describing the technical tasks to be conducted, the risks that are likely, the resources that will be required, the work products to be produced, and a work schedule. Modeling. When you are a landscaper, a bridge builder, an aeronautical engineer, a carpenter, or an architect. You work with models every day. You create a sketch of the things so that you will understand the big picture, what it will look like architecturally, how the constituent parts fit together, and many other characteristics. If required, you refine the sketch into greater and greater detail in an effort to better understand the problem and how you are going to solve it. A software engineer does the same thing by creating models to better understand software requirements and the design that will achieve those requirements. Construction. This activity combines code generation, either manual or automated, and the testing that is required to uncover errors in the code. Deployment. The software as a complete entity or as a partially completed increment is delivered to the customer who evaluates the delivered product and provides feedback based on the evaluation. These five generic framework activities can be used during the development of small, simple programs, the creation of large web applications, and for the engineering of large, complex computer-based systems. The details of the software process will be quite different in each case, but the framework activities remains the same. A stakeholder is anyone who has a stake in the successful outcome of the project. Business managers, end users, software engineers, support people, etc. Rob Thompson jokes that a stakeholder is a person holding a large and sharp stake. If you don't look after your stakeholders, you know where the stake will end up. Einstein argued that there must be a simplified explanation of nature because God is not capricious or arbitrary. No such faith comforts the software engineer. Much of the complexity that he must master is arbitrary complexity. Fred Brooks. For many software projects, framework activities are applied iteratively as a project progresses. That is, communication, planning, modeling, construction, and deployment are applied repeatedly through a number of project iterations. Each project iteration produces a software increment that provides stakeholders with a subset of overall software features and functionality. As each increment is produced, the software becomes more and more complete. Software engineering process framework activities are complemented by a number of umbrella activities. In general, umbrella activities are applied throughout a software project and help a software team manage and control progress, quality, change, and risk. Typical umbrella activities include software project tracking and control allows the software team to access progress against the project plan and take any necessary action to maintain the schedule. Risk management assesses risk that may affect the outcome of the project or the quality of the product. Software quality assurance defines and conducts the activities required to ensure software quality. Technical reviews assesses software engineering products assesses software engineering work products in an effort to uncover and remove errors before they are propagated to the next activity. Measurement defines and collects process, projects, and product measures that assist the team in delivering software that meets stakeholders' need. Can be used in conjunction with all other framework and umbrella activities. Software configuration management manages the effects of change throughout the software process. Reusability management defines criteria for work product reuse, including software components, and establishes mechanism to achieve reusable components. Work product preparation and production encompasses the activities required to create work products such as models, documents, logs, forms, and lists. Umbrella activities occur throughout the software process and focus primarily on project management, tracking, and control. Software process adaptation is essential for project success. How do process models differ from one another? Each of the umbrella activities is discussed in detail later in the book. Earlier in this section, I noted that the software engineering process is not a rigid description that must be followed dogmatically by a software team. Rather, it should be agile and adaptable to the problem, to the project, to the team, and to the organizational culture. Therefore, a process adopted for one project might be significantly different than a process adopted for another project. Among the differences are overall flow of activities, actions, and tasks, and the independencies among them. Degree to which actions and tasks are defined within each framework activity. Degree to which work products are identified and required. Manner in which quality assurance activities are applied. Manner in which project tracking and control activities are applied. Overall degree of detail and rigor with which the process is described. Degree to which the customer and other stakeholders are involved in with the project. Level of autonomy given to the software team. Degree of which team organization and rules are prescribed. I feel a recipe is only a theme which an intelligent cook can play each time with a variation. Madame Benoit. In part 1 of this book, I will examine software process in considerable detail. Uh, Prescriptive process model. Chapter 2 stress detailed definition, identification, and application of process activities and tasks. Their intent is to improve system quality, make projects more manageable, make delivery dates and costs more predictable, and guide teams of software engineers as they perform the work required to build its system. Unfortunately, there have been times when these objectives were not achieved. If prescriptive models are applied dogmatically and without adaptation, they can increase the level of bureaucracy associated with building computer-based system and inadvertently create difficulty for all stakeholders. Agile process models. Chapter 3 emphasize project agility and follow a set of principles that lead to a more informal but proponents argue no less effective approach to software process. These process models are generally characterized as agile because they emphasize maneuverability and adaptability. They are appropriate for many types of projects and are particularly useful when web applications are engineered. What characteristics an agile process characterizes? Software engineering practice in section 1.4.1 introduced a generic software process model composed of a set of activities that establish a framework for software engineering practice. Generic framework activities: communication, planning, modeling, construction, and deployment. And umbrella activities establish a skeleton architecture for software engineering work. But how does the practice of software engineering fit in? In the sections that follow, you will gain a basic understanding of the generic concepts and principles that apply to framework activities. You should revisit relevant sections within this chapter as specific software engineering methods and umbrella activities are discussed later in this book. A variety of thought-provoking quotes on the practice of software engineering can be found at www.literateprogramming.com. You might argue that Polya's approach is simply common sense. True, but it's amazing how often common sense is uncommon in the software world. The essence of practice. In a classic book, How to Solve It, written before modern computers existed, George Polya, Pol 45, outlined the essence of problem solving and consequently the essence of software engineering practice. Understand the problem, communication and analysis. Second, plan a solution, modeling and software design. Carry out the plan, code generation. Examine the result for accuracy, testing, and quality assurance. In the context of software engineering, these common sense steps lead to a series of essential questions adapted from Paul 45. Understand the problem. It's sometimes difficult to admit, but most of us suffer from hubris when we are presented with a problem. We listen for a few seconds and then think, "Oh yeah, I understand. Let's get on with solving this thing." Unfortunately, understanding isn't always that easy. It's worth spending a little time answering a few simple questions. Who has a stake in the solution to the problem? That is, who are the stakeholders? What are the unknowns? What data functions and features are required to properly solve the problem? Can the problem be compartmentalized? Is it possible to represent smaller problems that may be easier to understand? Can the problem be represented graphically? Can an analysis model be created? Plan the solution. Now you understand the problems, or so you think, and you can't wait to begin coding. Before you do, slow down just a bit and do a little design. Have you seen similar problems before? Are there patterns that are recognizable in a potential solution? Is there existing software that implements the data functions and features that are required? Has a similar problem been solved? If so, are elements of the solution reusable? Can sub problems be defined? If so, are solutions readily readily apparent for the sub problems? Can you present can you represent a solution in a manner that leads to effective implementation? Can a design model be created? Carry out the plan, the design. Okay, there is a grain of discovery in the solution of any problem. There is a grain of discovery in the solution of any problem. George Pulia. Carry out the plan. The design you have created serves as a roadmap for the system you want to build. There may be unexpected detours, and it's possible that you will discover an even better route as you go, but the plan will allow you to proceed without getting lost. Does the solution conform to the plan? Is source code traceable to the design model? Is each component part of the solution probably correct? Have the design and code been reviewed, or better, have correctness proofs been applied to the algorithm? Examine the result. You can't be sure that your solution is perfect, but you can't be sure that your solution is perfect, but you can be sure that you have designed a sufficient number of tests to uncover as many errors as possible. Is it possible to test each component part of the solution? Has a reasonable testing strategy been implemented? Does the solution produce results that conform to the data functions and features that are required? Has the software been validated against all stakeholder requirements? It should not surprise you that much of this approach is common sense. In fact, it's reasonable to state that a common sense approach to software engineering will never lead you astray. General principles. The dictionary defines the word principle as an important underlying law or uh, assumptions required in a system of thought. Uh, Throughout this book, I will discuss principles at many different levels of abstraction. Some focus on software engineering as a whole, others consider a specific generic framework activity, for example, communication, and still others focus on software engineering actions, for example, architectural design or technical tasks, for example, write a uses scenario. Regardless of their level of focus, principles help you establish a mindset for solid a software engineering practice. They are important for that reason. David Hooker, who 96 has the proposed 7 principles that focus on software engineering practice as a whole. They are reproduced in the following paragraphs. Advice: before beginning a software project, be sure the software has a business purpose and that users perceive value in it. The first principles: the reason it all exists. A software system exists for one reason: to provide value to its users. All decisions should be made with this in mind. Before specifying a system requirement, before noting a piece of system functionality, before determining the hardware problems or development processes, ask yourself questions such as: does this add real value to the system? If the answer is no, don't do it. All other principles support this one. The second principle, KISS: keep it simple, stupid. Um, exclamation mark. Software design is not a haphazard process. There are many factors to consider in any design effort. All design should be as simple as possible, but no simpler. This facilitates having sorry this facilitates having a yes this facilitates having a more easily understood and easily maintained system. This is reproduced with permission. What? Permission of the author. Who 96 Hooker defines patterns for these principles at http c2.com/cgi/wiki question mark 7 principles of software development. Not to say that this is not to say that features, even internal features, should be discarded in the name of simplicity. Indeed, the most elegant design are usually the more simple ones. Simple also does not mean quick and dirty. In fact, it often takes a lot of thought and work over multiple iterations to simplify. The payoff is software that is more maintainable and less error prone. The third principle, maintain the vision. A clear vision is essential to the success of a software project. Without one, a project almost unfailingly ends up being of two or more minds about itself. Without conceptual integrity, a system threatens to become a patchwork of incompatible designs held together by the wrong kind of screws. Compromising the architectural vision of a software system weakens and will eventually break even the well designed systems. Having an empowered architect who can hold the vision and enforce compliance helps ensure a very successful software project. There is a certain majesty in simplicity which is far above all the quaintness of wit. Alexander Pape, 1688 to 1744. The fourth principle, what you produce, others will consume. Seldom is an industrial strength software system constructed and used in a vacuum. In some way or other, someone else will use, maintain, document, or otherwise depend on being able to understand your system. So always specify, design, and implement knowing someone else will have to understand what you are doing. The audience for any product of software development is potentially large. Specify with an eye to the users. Design keeping the implementers in mind. Code with concern for those that must maintain and extend the system. Someone may have to debug the code you write, and that makes them a user of your code. Making their job easier adds value to your system. If software has value, key point, if software has value, it will change over its useful life. For that reason, software must be built to be maintainable. The fifth principle, be open to the future. A system with a long lifetime has more value in today's computing environments where specifications change on a moment's notice and hardware platforms are obsolete just a few months old. Software lifetimes are typically measured in months instead of years. However, true industrial strength software systems must endure far longer. To do this successfully, these systems must be ready to adapt to these and other changes. Systems that do this successfully are those that have been designed this way from the start. Never design yourself into a corner. Always ask what if and prepare for all possible answers by creating systems that solve the general problem, not just the specific one. This could very possibly lead to the reuse of an entire system. This advice can be dangerous if it is taken to extreme. Which advice? Always ask what if and prepare for all possible answers by creating systems that solve the general problem but not the specific one. This advice can be dangerous if it is taken to extremes. Designing for the general problem sometimes requires performance compromises and can make a specific solutions inefficient. The sixth principle, plan ahead for reuse. Reuse saves time and effort. Achieving a high level of reuse is arguably the hardest goal to accomplish in developing a software system. The reuse of code and designs has been proclaimed as a major benefit of using object oriented technologies. However, the return on this investment is not automatic. To leverage the reuse possibilities that object oriented or conventional programming provides requires forethought and planning. There are many techniques to realize reuse at every level of the system development process. Planning ahead for reuse reduces the cost and increases the value of both the reusable components and the systems into which they are incorporated. The seventh principle, think. Exclamation mark. Think this last principle is probably the most overlooked. Placing clear, complete thought before action almost always produces better results. When you think about something, you are more likely to do it right. You also gain knowledge about how to do it right again. If you do think about something and still do it wrong, it will become valuable experience. A side effect of thinking is learning to recognize when you don't know something, at which point you can research the answer. When clear thought has gone into a system, value comes out. Applying the first six principles requires intense thought, for which the potential rewards are enormous. If every software engineer and every software team simply followed Hooker's seven principle, many of the difficulties we experience in building complex computer-based systems would be eliminated. Software myths. Erroneous beliefs that software and the process that is used to build it can be traced to the earliest days of computing. Myths have a number of attributes that make them insidious. For instance, they appear to be reasonable statements of fact, sometimes containing elements of truth. They have an intuitive feel, and they are often promulgated by experienced practitioners who know the score. Today, most knowledgeable software engineering professionals recognize myths for what they are: misleading attitudes that have caused serious problems for managers and practitioners alike. However, old attitudes and habits are difficult to modify, and remnants of software myths remained. Although this is true for those who use the software on future projects, reuse can be expensive for those who must design and build reusable components. Studies indicate that designing and building reusable components can cost between 25 to 200% more than targeted software. In some cases, the cost differential cannot be justified. In the absence of meaningful standards, a new industry like software comes to depend instead of folklore. Tom DeMarco. Management myths. Managers with software responsibility, like managers in most disciplines, are often under pressure to maintain budgets, keep schedules from slipping, and improve quality. Like a droning person who grasps at a straw, a software manager also grasps at belief in a software myth, if that belief will lessen the pressure even temporarily. Myth. एक second. In the absence of meaningful standards, a new industry like software becomes to depend instead of folklore. Tom D. Marco. Web reference. The software project managers network at www.spmn.com can help you dispel these and other myths. Myth, myth. We already have a book that is full of standards and procedures for building software. Won't that provide my people with everything they need to know? Reality: the book of standards may very well exists, but is it used? Are software practitioners aware of its existence? Does it reflect modern software engineering practice? Is it complete? Is it adaptable? Is it streamlined to improve time to delivery while still um, maintaining a focus on quality? In many cases, the answer to all these questions is no. Myth: if we get behind schedule, we can add more programmers and catch up, sometimes called the Mongolian horde concept. Reality: software development is not a mechanistic process like manufacturing. In the words of Brooks, Bro 90 Bro 95, adding people to a late software project makes it later. Adding people to a late software project makes it later. At first, this statement may seem counterintuitive. However, as the new people are added, people who were working must spend time educating the newcomers, thereby reducing the amount of time spent on productive development effort. People can be added, but only in a planned and well coordinated manner. Myth: if I decide to outsource the software project to a third party, I can just relax and let them and let that firm build it. Reality: in an organization does not if an organization does not understand how to manage and control software projects internally, it will invariably struggle when it outsources software projects. Customer myths. A customer who requests a computer software may be a person at the next desk, a technical group down the hall, the marketing or sales department, or an outside company that has requested software under contract. In many cases, the software believes myths about software because software managers and practitioners do little to correct misinformation. Myths lead to false expectation by the customer and ultimately dissatisfaction with the developer. Work very hard to understand what you have to do before you start. You may not be able to develop every detail, but the more you know, the less risk you take. Myth. A general statement of objectives is sufficient to begin writing programs. We can fill in the details later. Reality. Although a comprehensive and stable statement of requirements is not always possible, an ambiguous statement of objectives is a recipe for disaster. Unambiguous requirements, usually driven iteratively, are developed only through effective and continuous communication between customer and developer. Myth. Software requirements continually change, but change can be easily accommodated because software is flexible. Reality. Is it true that software requirements change, but the impact of change varies with the time at which it is introduced? When requirements changes are requested early before design or code has been started, the code impact is relatively small. However, as time passes, the cost the cost impact is relatively small. However, as time passes, the cost impact grows rapidly. Resources have been committed, a design framework has been established, and change can cause upheaval that requires additional resources and major design modifications. Advice: whenever you think we don't have time for software engineering, ask yourself, will we have time to do it over again? Practitioners practitioners time Practitioners myths that are still believed by software practitioners have been fostered by over 50 years of programming culture. During the early days, programming was viewed as an art form. Old ways and attitudes die hard. Myth. और से die बहुत ही मुश्किल से मरते हैं old ways और attitudes. Myth. Oh, once we write the program and get it to work, our job is done. Reality. Someone once said that the sooner you begin writing code, the longer it will take you to get done. Industry data indicate that between 60 and 80% of all effort expended on software will be expended after it is delivered to the customer for the first time. Myth. Until I get the program running, I have no way of assessing its quality. Reality. One of the most effective software quality assurance mechanisms can be applied from the inception of a project: the technical review. Software reviews described in chapter 15 are a quality filter that have been found to be more effective than testing or finding certain classes of software defects. The only deliverable work product for a successful project is the working program. Reality. A working program is only one part of a software configuration that includes many elements. A variety of work products, for example, models, documents, plans, provide a foundation for successful engineering and more important guidance for software support. Myth. Software engineering will make us create a voluminous and unnecessary documentation and will invariably slow us down. Reality. Software engineering is not about creating document, it is about creating a quality product. Better quality leads to reduced rework, and reduced rework results in faster delivery times. Many software engineering engineers have adopted an agile approach that accommodates change incrementally, thereby controlling its impact and cost. Agile methods are discussed in chapter 3. Many software professionals recognize the fallacy of the myths just described. Regrettably, habitual attitudes and methods foster poor management and technical practices. Even when reality dictates a better approach, recognition of software realities is the first step toward formulation of practice formulation of practical solution for software engineering. How it all starts. Every software project is precipitated by some business need, the need to correct a defect in an existing application, the need to adapt a legacy system to a changing business environment, the need to extend the functions and features of an existing application, or the need to create a new product, service, or system. At the beginning of a software project, the business need is often expressed informally as part of a simple conversation. The conversation presented in the sidebar is typical. Safe home. How a project starts. The scene. Meeting root. अच्छा एक सेकंड नीचे. अच्छा. The safe home project will be used throughout this book to illustrate the inner workings of a project team as it builds a software product. The company, the project, and the people are purely fictitious, but the situations and problems are real. Safe home. The scene. Meeting room at a CPI Corporation, a fictional company that makes consumer products for home and commercial use. The players. Mal Golden, Senior Manager, Product Development; Lisa Perez, Marketing Manager; Lee Warren, Engineering Manager; Joe Camilleri, Executive VP, Business Development. The conversation. Joe: okay, Lee, what's this? I hear about your folks developing a what? A generic universal wireless box. Lee: it's pretty cool, about the size of a small matchbox. We can attach it to sensors of all kinds, a digital camera, just about anything, using the 802.11g wireless protocol. It allows us to access the device output without wires. We think it will lead to a whole new generation of products. Joe: you agree? Mal: I do. In fact, with sales as flat as they have been this year, we need something new. Lisa and I have been doing a little market research, and we think we have got a line of products that could be big. Joe: how big? Bottom line big. Mal: avoiding a direct commitment. Tell him about our idea, Lisa. Lisa: it's a whole new generation of what we call home management products. We call them safe home. They use the new wireless interface, provide homeowners or small business people with a system that is controlled by their PC. Home security, home surveillance, appliance and device control. Turn down the home air conditioner driving home and while you are driving home, that sort of thing. Lee jumping in. Engineering's done a technical feasibility study of this idea. Joe: it's doable at low manufacturing cost. Most hardware is off the shelf. Software is an issue, but it's nothing that we can't do. Joe: interesting. Now I asked about the bottom line. Mal: PCs have penetrated over 70% of all households in the USA. If we could price this thing right, it would be a killer app. Nobody else has our wireless box. It's proprietary. We all have a 2 year jump on the competition revenue, maybe as much as 30 to 40 million dollars in the second year. Joe is smiling. Let's take this to the next level. I'm interested. With the exception of a passing reference, software was hardly mentioned as part of the conversation, and yet software will make or break the safe home product line. The engineering effort will succeed only if safe home software succeeds. The market will accept the product only if the software embedded within it properly meets the customers as yet unstated needs. We all follow the progression of safe home software engineering in many of the chapters that follow. Summary is the key element in the evolution of computer based system and products, and one of the most important technologies on the world stage. Over the past 50 years, software has evolved from a specialized problem solving and information analysis tool to an industry in itself. Yet, we still have trouble developing high quality software on time and within budget. Software programs, data, and descriptive information addresses a wide array of technology and application areas. Legacy software continues to present special challenges to those who just maintain it. Web based systems and applications have evolved from simple collections of information content to sophisticated systems that present complex functionality and multimedia content. Although these web apps have unique features and requirements, they are softwares they are software none nonetheless they are software nonetheless. Okay, software engineering encompasses process methods and tools that enable complex computer-based systems to be built in a timely manner with quality. The software process incorporates five framework activities: communication, planning, modeling, construction, and deployment, that are applicable to all software projects. Software engineering practice is a problem-solving activity that follows a set of core principles. A wide array of software myths continue to lead managers and practitioners astray, even as our collective knowledge of software and the technologies required to build it grow. As you learn more about software engineering, you will begin to understand why these myths should be debunked whenever they are encountered. Part 1: The software process. In this part of software engineering, a practitioner's approach, you will learn about the process that provides a framework for software engineering practice. These questions are addressed in this chapter and that follow. What is a software process? What are the generic framework activities that are present in every software process? How are processes modeled and what are process patterns? What are the prescriptive process model that and and what are their strengths and weaknesses? What is agility, a watchword in modern software engineering work? What is agile software development and how does it differ from more traditional process models? Once these questions are answered, you will be better prepared to understand the context in which software engineering practice is applied. Process model. In a fascinating book that provides an economist's view of software and software engineering, Howard Beecher Jr. BE 98 comments on the software process. Because software, like all capital, is embodied knowledge, and because that knowledge is and because that knowledge is initially dispersed, tacit, latent, and incomplete in large measure, software development is a social learning process. The process is a dialogue in which the knowledge that must become the software is brought together and embodied in the software. The process provides interaction between users and designers, between users and evolving tools, and between designers and evolving tools technology. It is an iterative process in which the evolving tool itself serves as the medium for communication each new record with each new round of the dialogue eliciting more useful knowledge from the people involved. Indeed, building computer software is an iterative social learning process, and the outcome, something that Beitzer, Beitzer would call software capital, is an embodiment of knowledge collected, distilled, and organized as the process is conducted. Quick look. What is it? when you work when you work to build a product or system, it's important to go through the series of predictable steps, a roadmap that help you create timely high quality result. The roadmap that you follow is called a software process. Who does it? Software engineers and their managers adapt the process to their needs, and then follow it. In addition, the people who have requested the software have a role to play in the process of defining, building, and testing it. Why is it important? Because it provides stability, control, and organization to the activity that can, if left uncontrolled, become quite chaotic. However, a modern software engineering approach must be agile. It must demand only those activities, controls, and work products that are appropriate for the project team and the product that is to be produced. What are the steps? At a detailed level, the process that you adapt depends on the software that you are building. The one process might be appropriate for creating software for an aircraft avionics system, while an entirely different process would be indicated for the creation of a website. What is the work product? From the point of view of a software engineer, the work products are the programs, documents, and data that are produced as a consequence of the activities and tasks defined by the process. How do I ensure that I have done it right? There are a number of software process assessment mechanisms that enable organizations to determine the maturity of their software process. However, the quality timeliness and the long-term viability and the product you build are the best indicators and the efficacy of the process that you are. But when exactly is a software process from a technical point of view? Within the context of this book, I define a software process as a framework as a framework for the activities, actions, and and tasks that are required to build high quality software. Is processing synonymous with software engineering? The answer is yes and no. A software process defines the approach that is taken as software is engineered, but software engineering also encompasses technologies that populates the process, technical methods, and automated tools. More important, software engineering is performed by creative, knowledgeable people who should adapt a mature software process so that it is appropriate for the products that they built and the demand of their marketplace. 2.1 2.1 A generic process model. In chapter 1, a process was defined as a collection of work activities, actions, and tasks that are performed when some work product is to be created. Each of these activities, actions, and tasks reside within a framework or model that defines their relationship with the process and with one another. The software process is represented schematically in figure 2.1. Referring to the figure, each framework activity is populated by a set of software engineering actions. Each software engineering action is defined by a task set that identifies the work tasks that are to be completed, the work products that will be produced, the quality assurance points that will be required, and the milestones that will be used to indicate process progress. As I discussed in chapter 1, a generic process framework for software engineering defines five framework activities: communication, planning, modeling, construction, and deployment. In addition, a set of umbrella activities: project tracking and control, risk management, quality assurance, configuration management, technical reviews, and others are applied throughout the process. You should note that one important aspect of the software process has not yet been discussed. This aspect, called process flow, describes how the framework activities and the actions and tasks that occur within each framework activity are organized with respect to sequence and time, and is illustrated in figure 2.2. Point. The hierarchy of technical work within the software process is activities encompassing actions populated by tasks. We think that the software developers are missing a vital truth. Most organizations don't know what they do. They think they know, but they don't know. Tom D. Marco. A linear process flow executes each of the five framework activities in sequence, beginning with communication and culminating with deployment. An iterative process flow repeats one or more of the activities before proceeding to the next. An evolutionary process flow executes the activities in a circular manner. Each orbit through the five activities leads to a more complete version of the software. A parallel process flow executes one or more activities in parallel with other activities. Modeling for one aspect of the software might be executed in parallel with construction of another aspect of the software. A सॉफ्टवेयर प्रोसेस फ्रेमवर्क सॉफ्टवेयर प्रोसेस फ्रेमवर्क उसके अंदर अम्ब्रेला एक्टिविटीज़ फिर अम्ब्रेला एक्टिविटी के अंदर फ्रेमवर्क एक्टिविटी हैशटैग 1 सॉफ्टवेयर इंजीनियरिंग एक्शन हैशटैग 1.1 टास्क सेट्स वर्क प्रोडक्ट्स क्वालिटी एश्योरेंस पॉइंट्स प्रोजेक्ट माइलस्टोन देन कंटिन्यूड सॉफ्टवेयर इंजीनियरिंग एक्शन हैशटैग 1.k टास्क सेट्स वर्क प्रोडक्ट्स क्वालिटी एश्योरेंस पॉइंट्स project milestone. Then it is continued framework activity hashtag n. In that software engineering action hashtag n.1 task set task sets work tasks work products quality assurance points project milestones. Software engineering action hashtag n.m task sets work tasks work products quality assurance points project milestones. Defining a framework activity. Although I have described five framework activities and provided a basic definition of each in chapter 1, a software team would need significantly more information before it could properly execute any one of these activities as part of the software process. Therefore, you are faced with a key question: what actions are appropriate for a framework activity given the nature of the problem to be solved, the characteristics of the people doing the work, and the stakeholders who are sponsoring the project. Process flow. Okay, process flow. uh, linear process flow. First it will come to communication, then it will go to planning say modeling say construction, and construction say deployment. Communication say planning say modeling say construction say deployment. Linear process flow. Then iterative process flow. लीनियर वाला बना दो पहले, कम्युनिकेशन से प्लानिंग से मॉडलिंग से कंस्ट्रक्शन से डिप्लॉयमेंट। फिर प्लानिंग के बाद फिर से कम्युनिकेशन में लूप जाएगा, कंस्ट्रक्शन के बाद फिर से कम्युनिकेशन में लूप जाएगा, मॉडलिंग में लूप रहेगा, मॉडलिंग होता रहेगा मॉडलिंग। ये है इटरेटिव प्रोसेस फ्लो। कम्युनिकेशन प्लानिंग मॉडलिंग कंस्ट्रक्शन डिप्लॉयमेंट पर लीनियर बना दो, फिर प्लानिंग से कम्युनिकेशन में ले जाओ लूप, कंस्ट्रक्शन से ले जाओ कम्युनिकेशन में लूप, फिर मॉडलिंग में मॉडलिंग का ही रूप रहने दो। उसके बाद है इवोल्यूशनरी प्रोसेस फ्लो। सबसे पहले कम्युनिकेशन में आएगा, कम्युनिकेशन से जाएगा प्लानिंग से जाएगा मॉडलिंग से जाएगा कंस्ट्रक्शन से जाएगा डिप्लॉयमेंट में, और डिप्लॉयमेंट से जाएगा फिर से कम्युनिकेशन में, और डिप्लॉयमेंट से एक और निकलेगा इंक्रीमेंट रिलीज। उसके बाद है पैरेलल प्रोसेस फ्लो। सबसे पहले आएगा कम्युनिकेशन में, फिर जाएगा प्लानिंग में, फिर कम्युनिकेशन और प्लानिंग दोनों से निकलता हुआ जाएगा मॉडलिंग में, फिर मॉडलिंग से निकल के जाएगा कंस्ट्रक्शन में, कंस्ट्रक्शन से निकल के जाएगा डिप्लॉयमेंट में, फिर डिप्लॉयमेंट से बाहर निकल जाएगा। और टाइम हमारा जा रहा है कंस्ट्रक्शन से लेकर डिप्लॉयमेंट की तरफ, कम्युनिकेशन से लेकर डिप्लॉयमेंट की तरफ। ये हो गया पैरेलल प्रोसेस फ्लो। 4 प्रोसेस फ्लो देख लिए, लीनियर प्रोसेस फ्लो, इटरेटिव प्रोसेस फ्लो, इवोल्यूशनरी प्रोसेस फ्लो, पैरेलल प्रोसेस फ्लो। For a small software project requested by one person at a remote location with simple, straightforward requirements, the communication activity might encompass little more than a phone call with an appropriate stakeholder. Therefore, the only necessary action is phone conversation, and the task set and this action encompasses are: make contact with a stakeholder via telephone, discuss requirements and take notes, organize notes into a brief written statement of requirements, email to a stakeholder to review and approval. If the project was considerably more complex with many stakeholders, each with a different set of something conflicting requirements, the communication activity might have 6 distinct actions described in chapter 5: inception, elicitation, elaboration, negotiation, specification, and validation. Each of these software engineering actions would have many work tasks and a number of distinct work products. Point: different projects demand different task sets. The software team choose the task set based on problem and project characteristics. Identifying a task set.